Welcome! It's a video lecture. We got to do things a little differently because of Hurricane Irma, Tropical Storm Irma, Tropical Depression Irma. I hope that you guys fared okay. Hope your houses are okay. Hope your neighborhoods are okay. And I look forward to seeing you next week. And once your power's back on and you're able to look at this video, I hope it helps you out a little bit with the Chapter 3 material. I know that it says week 2 on your Unit 1 assignment, and you might be able to get into some of those problems after this video lecture. If you start looking at the end of chapter questions for Chapter 3 and you still feel fuzzy and not quite clear based on your reading and what I talk about today, it's okay because we'll sort out whatever confusion you have next week. So I hope that everybody will have their book and have been able to read and do the practice problems in the book. And we're going to practice problems today together. And between all that, I am wishing that we get off to a good start this semester despite the crazy weather. So with that in mind, let's talk about where we were last week at LEAD or HEGA, because I might do this lecture for both if my HEGA people and I can't get together on Thursday. So we left off talking about speed, distance over time. We discussed different units for speed, meters per second, kilometers per hour, and miles per hour. And we talked about the difference between instantaneous and average speed. Instantaneous speed was that glance at the speedometer speed. How fast am I going right now? And average speed was more of a big picture. How fast were we going for the entire trip on average? So you might have gone an average of 30 miles per hour, but during that trip time, you might have gone 0 miles per hour and 50 miles per hour as your instantaneous speeds. Today, what I want to talk about is how speed is different from velocity. If you've read Chapter 3, you have read the word velocity a lot. And velocity and speed are different. One of them is a scalar, and one of them is a vector. So the definition of a scalar is that it's just a number. Why don't they call it just a number? Because they have to give it a fancy science name. Scalar means number, and then a vector has both a number and a direction associated with it. So it's not just a size or a magnitude, but it's also got direction. It could be going up or it could be going down. It could be going east or it could be going west. East, west for you guys. So that's the difference between the two. I'm going to give you a packet when we get together again. I might email it out this week if for those of you that want to look at it and get a little ahead. But let's go ahead and get some scalars written down and some vectors written down. So scalar, speed is a scalar. That's the first one that we talked about last week. If you're going 55 miles per hour, you're just going 55 miles per hour. We don't know if you're going north. We don't know if you're going south. We don't know if you're going northeast or southwest. We just know that you're going 55 miles per hour. Another scalar is time. When we state how long it takes to do something, 30 seconds, an hour, 3 days, we don't ever put a direction on that. We don't say that it takes 3 seconds north, or we don't say it takes 3 days up. We just say the time as a number only. So it's a scalar. Mass is a scalar. It's just a number. The mass of an object, whether you do it in grams or kilograms, would be a scalar quantity, only a number. You guys can think of some more scalars if you'd like on your own. The book, I'm trying to remember if there's questions in the book about it, but I know I put some on the packet. So you'll get an opportunity to sort out scalar vector in the linear motion packet that you'll get on next week. Vector. So speed is a scalar, and its vector equivalent is velocity. To be absolutely proper, we want to always express velocity with a direction. So in some of the problems you work, it'll say find the magnitude of velocity. Some students get confused and they're like, I don't understand how to find magnitude. We don't have an equation that has magnitude in it. Magnitude just means the number. find the size of it. How big is it? How big is our velocity? Is it 10 meters per second? Is it 20 kilometers? And then the direction would be north, south, east, west, or it could be up, could be down. So those are directions that you would see on a velocity vector. Another vector that we're going to do is force. And we will do that in the second unit. We'll talk about forces. Oh, I've almost forgot one that we're going to talk about maybe at the end of this video, maybe next week in class. We'll see how long I feel like videoing myself. Acceleration is also a vector. So it has both a magnitude, a number, and a direction associated with it. We're going to discuss a lot in the coming weeks about the direction of these two. How you can have velocity going to the right and how you can have acceleration going to the left, and what that does. Does it make the velocity get bigger? Does it make it get smaller? We're going to throw things up in the air. We're going to talk about what happens when the object is going up. Its velocity is getting smaller. That's because the acceleration vector is pointing down. That's gravity. So that's how we sort of sort out scalars versus vectors. The last one that I want to put up here, I just want to mention, I'm not going to talk about it a whole lot because honestly in this class we're going to use them a little interchangeably. But the distance, when we did speed equals distance over time last week, technically all those numbers are scalar numbers. They don't have directions associated with them. In physics there's a type of distance, a special type of distance called displacement. I'm going to try to pick this up so I can write on the board. This is awkward. I can't write right at the bottom. There we go. Okay, I don't know if you can see that. Displacement. So displacement is a special kind of distance, and it's a vector. It has a direction associated with it, and we use it to describe how our position is changed. I'm going to give you an example, and I'm going to erase the board, and then I will draw you some pictures to explain the difference between displacement and distance. All right, so I got a little ant, and the ant's going to crawl 10 meters east, and then he's going to turn around, and he's going to crawl 6 meters west. So his initial distance is this way, and then his final distance is back to the west. So if I ask you to tell me how much distance he covered, that's pretty easy, right? You would say he went 10 meters and then he went another 6 meters. So that would be 16 meters. Pretty straightforward, right? And then we do the physics part and we say, well, what is his displacement? When we ask about the displacement of the ant, we then want to look at these arrows and their directions as being the vectors that represent our overall displacement. Now, if he had a displacement, this is where he started, and then he went over here to the 10 meters east, and then he turned around and went 6 meters west, his overall displacement, comparing where he started to where he finished, would look like this. So it would be a vector that goes from where he began to where he finished. It doesn't take into account how he got there. He actually could have crawled up here and then around in a loop and then come back down and then gone all the way over here and ended up in the same place. And his displacement would have been exactly the same as if he just went 10 to the west and 6 to the east. I've got that backwards, 10 to the east and 6 to the west. So if we look at these as vectors, you want to think about them like a number line. If we go to the right, it's positive. If we come to the left, it's negative. So when you do vector addition, you always want to look at the direction. And then you want to think, well, this is almost like a negative number because it's going the opposite direction or to the left. So you would really say 10 meters east minus 6 meters west. And that would be 4 meters to the east. So that's the answer for the displacement of the ant. He ended up 4 meters east of where he started. So we have a magnitude, that's the number, and a direction, that's the east. That's the difference between distance and displacement. And that's how you handle the difference between scalar quantities and vector quantities. Now let's talk about velocity a little more, because velocity can work the same way. And we can look at velocities relative to a frame of reference. That sounds fancy, doesn't it? And then we can figure out how to add them together and subtract them. They do a little bit of this in the book. They talk about relative velocity. So if you have, I believe the problems in the book chapter have a train car, and the train car is on tracks and it's moving 10 meters per second. We'll say that. We'll just go with our directions we've been using, east. And then there'll be somebody who is on the train car and that person might be also moving in the same direction. So the train car is moving 10 meters per second to the east, and the person is also moving 3 meters per second to the east. Does the person on the train car feel like they're going 13 meters per second? Or do they just feel like they're going 3 meters per second? It's hard to say. They might get a little dizzy walking, but a lot of times if you're on something that's already moving, like a bus or a train or a plane, you can't really tell that your speed is so much larger based on the speed of the train. It just feels like you're walking on a regular non-moving surface. So if you were talking about somebody standing off to the side and watching this person go by, they would say that the speed of the person on the train is 10 plus 3. 13 meters per second. What if the person on the train turned around and decided to go in a different direction? What if now they decided they were going to turn around and walk backwards at 4 meters per second? So we've got this guy standing on the side of the train tracks. He's watching the car go 10 meters per second east, and he's watching the person walk backwards relative to the car 4 meters per second. If he just focused on the person, then their speed would be 10 meters per second minus 4 meters per second. And that would be 6 meters per second. Now, I forgot something. If this is velocity, do I have everything I need here? Because I have some directions. Don't I need a direction with my velocity? Velocity should include the number, the magnitude, and the direction. So this 10 plus 3, when he was going in the same direction of this train, that should be east. And then is this still east? Is the guy running in the totally different direction to the west, or is he just going a little less slow than the train itself, but in the same direction? the east is still bigger than the west. So he's going to end up going east here as well. It's just a smaller magnitude. So those are two examples with displacement and velocity of how we can add and subtract vectors to get an answer. The math is not too complicated. You're either saying plus or minus. I'm not going to do any Pythagorean theorem adding vectors going in different directions at this point. So we're just going to keep it simple. Plus, minus. If they're going in the same direction, we want to add them together. And if they're going in opposite directions, we want to subtract them. And with that, I think we're ready to talk about some sample velocity calculations. Now we're going to practice working some problems with velocity, distance, and time. On my piece of paper, I have the equation that's on your Unit 1 assignments sheet. Distance equals velocity times time. And some students are very comfortable with this. They can take two givens and solve for an unknown. And some students are a little less comfortable with the algebra, and they like to rely on the triangle form for this equation. Here's how this triangle form works. I have a D on the top with a line, and then underneath I have V times T. If I'm looking for distance in this equation, it's pretty easy to see that it's velocity times time. If I want to use the triangle to figure that out, then if you're looking for D, you cover up the distance, and then there's a giant shadow in the way, but let me use my pen. If you cover up the distance, then what you'll do is take velocity times time. The ones that students have a harder time with is if they're solving for V or T. The triangle is nice because in that case you just cover up the thing you want to find. So if you want to find velocity, you cover that up. And the equation to find velocity is distance divided by time because it's D over T. If you're trying to find the time in this equation, you cover up the T, and then you would take distance divided by velocity. Some of the equations we use in physics, you can use this triangle method if you're not as comfortable with algebra to find your unknown. Our first question, a beetle crawls 8.5 meters in 72 seconds. What is its velocity? This question is a very basic question. We're looking for one variable, and they've given us numbers for the other two. The thing that you want to try to accomplish here is to first identify the numbers that you were given. 8.5 meters. Meters is a measurement of distance. So we're going to write down our first given. Distance equals 8.5 meters. Now we're going to look at the rest of the question. He crawls 8.5 meters in 72 seconds. Most people are able to recognize seconds as being a unit of time. So we're going to label that as a T. The key to these questions is looking at the unit and deciding which of these variables up here that it is. So meters, kilometers, miles, those are going to be distance measurements, and then seconds, minutes, hours, those are going to be time measurements. The question wants us to find the velocity, so that is obviously our V. Once we know what we're looking for and what we have to work with, we can sort out which equation to use. Now, so far we only have one equation to use, so the question is not too difficult to answer. In trying to figure out how to solve for that, you can use the triangle and cover up the V and know to take distance divided by time. For those of you more comfortable with algebra, solving for V over here isn't too bad either. You just take distance and you divide by the time to get the V by itself. So for this problem, we'll have 8.5 meters divided by 72 seconds, and we will get, using a calculator please, because this is not an easy one to do in your head, 0.12 meters per second. The unit on our answer is important. You don't want to ever give a naked number without a unit, and we get the unit for this by taking meters over seconds. If we had had kilometers over hours, then our unit would have been kilometers per hour. But this question gave us meters and seconds, so our velocity unit is in meters per second. The next question is about a hurricane, because we've had a lot of that to deal with this week. A hurricane moves north at 23 kilometers per hour. How long will it take the storm to travel 580 kilometers? So let's look at our two numbers and let's label what they are. Kilometers per hour is our first unit. This unit is a distance per time unit, and that means it is a velocity. Our next number that we were given is 580 kilometers, and kilometers, it's not a time, it's not a velocity, it is a distance. The question asks how long. Now, if I asked how long your foot was, that would be a distance measurement. But in physics, when we ask how long something is, a lot of times we're asking for time, and this wants to know how long it will take for the storm to reach us. So that is a time question. Let's look back up. We are looking for t, and let's slide back up to the top of our page. If we're looking for t, and you're comfortable with this equation set up this way, then you can just divide both sides by v. If you're not comfortable with the algebra, you just cover up your t in the triangle and you take distance over v, or distance divided by velocity. So the equation that we'll use is t equals distance divided by velocity. Now, if those units in there seem confusing, don't worry about that. You can just take 580 and divide it by 23. And when you put that in your calculator, you will come out with an answer of 25. We want to be sure not to leave a naked number. So glance back at what you're solving for. Solving for time. And we have to say, well, is it seconds? Is it minutes? Is it hours? Does anybody see it? Can you find it? It's right here. Kilometers per hour. So if we are measuring our velocity or speed in kilometers per hour, then the time that we get when we put the one over the other will be in hours. So the answer to this question is 25 hours. Our last practice problem is about Sarah. If Sarah can run 2.8 meters per second for 60 minutes, how far will she have gone? Let's take a look at our given information. 2.8 meters per second. That sounds like a velocity measurement to me because it's distance over time. So that's our velocity. And then 60 minutes. It's not just the name of a TV show. It's also a unit of time. Now this is a little tricky. So check this out. We have seconds in our velocity unit, and now we have minutes. Those do not match. So we have to fix it. I think fixing the velocity unit will be kind of complicated. So I don't think we should turn this into meters per minute, but we can probably change 60 minutes into seconds. Everybody knows that there are 60 seconds in every minute. So that's going to give us a total time of 3,600 seconds. We have velocity and time, and the question is asking how far. So they're asking us to find distance. We have a V and we have a T, and we're looking for D. So look back up here. Whoops. If we're looking for D, this is the easy one, right? We just say velocity times time. Alternatively, you can take your pen, cover up the D in the triangle, and it'll tell you the same thing. Velocity times time. Distance equals VT. So we'll take 2.8 and we're going to use the 3600 seconds. And we'll find that the distance is equal to 10,000 meters, or a 10K. If you accidentally missed that little time conversion and you said 2.8 times 60, you're only going to lose a point on a test. So no worries if you forget to convert, but if you want to get it perfectly right, then be sure that the time in your velocity matches the time unit itself. Hi, I'm going to try this one more time. I'm having a lot of issues videoing. This will be the last section of the video. We have discussed velocity. We discussed calculating with velocity. We talked about vectors, displacement, and distance. And now I want to introduce acceleration. We'll finish up talking about acceleration of different kinds on our class day next week. So if I have a car and it's got its cruise control set, meaning that it's on an interstate and it's set a specific speed in the speedometer of 10 meters per second, which we don't have on our speedometers, but let's just play along. That would be an example of having a constant speed or a uniform speed. A constant speed implies that it's not changing. It's not changing to 11 or 12. It's not dropping to 9 or 8 or 0. It's just 10 meters per second. But is the velocity of the car constant? That's the real question. In order for the velocity of this car to be constant, we would need two things to remain the same. Velocity is a vector and speed is a scalar. So the scalar speed, we just need that number to stay the same. But for velocity to stay constant, we need both the number or magnitude and the direction of the vector to stay constant. In Georgia, it's very rare for us to have a car with cruise control set that maintains a constant velocity because it's on a curvy road. We have roads that curve left and right. But if we were driving the car out in Texas or Colorado, Wyoming, Montana, we might drive on a very straight road with no left or right turns, no arcs in any direction for a long time, in which case the speed of the car and the direction of the car would be constant. So I'm going to pretend we're out west where the roads are straight, the skies are big, and I'm going to say that this car has a constant velocity, meaning a constant speed and a constant direction. Let's look at our Ferris wheel down here. Our Ferris wheel is on, it's in motion, and it's going a constant speed of 3 meters per second. It's not speeding up to 4 or 5 meters per second. It's not about to slow down to let passengers off. Is it going a constant velocity? In any circular motion where you're going around in a circle, the direction that the cars are going is constantly changing. Sometimes they're going to the right, sometimes to the left, sometimes up, sometimes down. So this is a changing velocity. Since the direction is changing, the velocity changes. I'll say it's not constant. So a constant velocity means constant speed and constant direction. A changing velocity could mean the speed is changing, but it also could just mean that the direction's changing, that the object is moving in a circular path. It doesn't have to maintain a perfect circle. It could just be a car going around turns on the road. All of these things where the direction or the speed are changing are describing a state of acceleration. And acceleration is when you have any change in velocity. If this car were to suddenly decide they needed to get somewhere quicker and crank their cruise control up a few meters per second and go to 15 meters per second or 18 meters per second, that would be a change in velocity. The acceleration would be occurring because there was an increase in velocity. If the car saw a deer and had to slow down or come to a stop, that would also imply there's a change in velocity because the speed decreased. So if the velocity decreases or the speed, the magnitude of that vector decreases, that would be an acceleration. And the Ferris wheel, even though the speed isn't changing, even though it's just the direction that's changing, that is still an acceleration. That doesn't mean the Ferris wheel is getting faster and faster and faster and faster and turning into some nightmare ride that you might see in a movie or read about in a book. It just means that the acceleration that it's occurring has to do with circular motion. It's called centripetal acceleration, and we'll learn about that later on in the semester. I want to discuss quickly the vector nature of acceleration and velocity and how they work together. But I'm going to pause it for a second so I can make sure this part of the video is recording. Hello. Okay, so back to our acceleration discussion. Acceleration is a change in velocity. And more specifically, here's an equation for you. So I want you to understand conceptually that whenever there's a change in velocity, either the magnitude, the speed part, or the direction, there's acceleration. But it's also an equation. And I have written here A, acceleration equals delta V, which is the change in velocity. Whenever you see a delta, it means change. So if we put the change in velocity over the time, more specifically, we can write the final velocity minus the initial velocity over time. Then we can actually calculate a number for acceleration. I have a car up here, and I have an initial velocity, VI, for my car is 10 meters per second. The final velocity is 20 meters per second. And it took a time of 10 seconds for that change to happen. So we can calculate the acceleration of the car. We can take our final, which is 20, minus the initial of 10, and divide by time. That's pretty easy math, right? 20 minus 10 is 10, and then we don't even need a calculator for the last part. That's just going to equal 1, and the unit's going to be a little weird. We got meters per second per second. So we're going to say that's meters per second squared. The unit for velocity is meters per second, and hopefully by now you're getting used to that a little bit. This is a little strange with a squared, but just know that's the unit for acceleration. 1 meter per second squared means that every second this car is driving during the time period, it gains 1 meter per second, which makes sense. If it was going 10, and then you wanted to know how long it took to get to 20, and you knew every second it was gaining 1 meter per second, then that would take you 10 seconds. I want to point out, too, that this is a positive 1, and that these were both positive velocities. And here's what this means about the vectors, because we learned velocity is a vector, but also is acceleration. It's a vector as well. And if the velocity is increasing and we get a positive acceleration, that means that the acceleration is going to the right, just in the exact same direction as the velocities are. And we're going to find the opposite is true when things are slowing down. All right, let's do a slowing down question. Let me erase this. And let's erase this vector for A. And then let's erase our math. Now let's consider a situation where the car was going 10 and it came up on some traffic, and now it's just going to be going 5 meters per second. We'll go ahead and keep the same time in there to keep it simple, and we'll do math with this new set of numbers. So now our final velocity is 5. Our initial velocity is 10. And our time is still 10 seconds. 5 minus 10 is not positive 5. It is negative 5. And that is going to end up being negative 0.5. And I'll squeeze in the meter per second squared, just so I won't leave the number naked. I don't want to see any naked numbers. Negative 0.5. What in the world does that mean to get a negative number? This means deceleration. So when you see a negative acceleration, it's a fancy way of saying that the object is decelerating. So acceleration means increasing velocity, deceleration means decreasing velocity. The negative also tells you which way the vector would go. If this is positive 10 and positive 5 and they're going to the right, the negative tells you it's going to the left. So our acceleration vector here is in the opposite direction of motion. Now this is really important conceptually, and hopefully you'll carry that with you to the class next week, because we're going to talk about how gravity can slow things down as they're flying up in the air, and that's what causes them to lose speed. But that same downward gravity makes them gain speed as they're falling. Really common sense things that we all understand, but we don't always understand mathematically, but you will after we get done with class next week. I think I'll leave it at that, and I will plan to see y'all in classrooms with electricity and your bright smiling faces at the next class. Take care.